What is your area of expertise, and then what is the type of research your lab does?
Yeah. Yeah. So the general topic or the general gist of what we do in our lab is to create devices that intimately integrate with biology, whether that's uh, humans or small animal subjects. Um, it really depends on the particular application. So the core strength of the group is soft materials, soft electronic materials, wireless power transfer, and design of devices to integrate with biology. So we leverage that in, for example, wearable devices and also implantable devices. And they serve as conduits or interfaces to various types of organ systems.
Right. And something that I've been talking about earlier is that biomedical engineering is so broad, but then even the subdisciplines within that, like biosensors, are
Yeah,
still completely broad
yeah.
themselves. And your lab is biosensors, but it's focused on implantables and wearables, and then anything else?
Yeah, we do sensors, right? That's an important part of what we do in the wearable and implantable space. However, we also make stimulators actually. So we don't only sense, we also stimulate and we compute at the same time. So it is not necessarily just biosensors that I would categorize our group into.
Right. And then there's also a bit of biomaterials coming in just because it's interacting with the soft materials, like you said.
Yeah, so yes and no. We look at the interfaces of soft materials and biology in general, but we don't create biomaterials themselves we don't grow cells in our lab, for example, but we look at, for example, what kind of cells grow around our devices and how can we, change mechanics to make them more palatable for the biological system that we stick them into. So there's certain aspects that we look into.
Awesome. And then, okay, so your lab and yourself have produced a lot of really high impact papers. There's a lot of
Yeah.
really cool journals out there. Do you have any tips for graduate students looking to make impactful research?
Yeah, I think there's a couple of components to this, right? In order to place your work in these type of journals, it first needs to be very rigorous, right? Often you can combine 3, 4 smaller papers into one of those, and then you kind of reach the level in order to get into the top tier of journals. That's one of the aspects. But there's also the topic, right? It needs to be significant to a variety of communities, scientific communities, and also the broader public. So those things need to come together to make an article that gets highly cited and therefore also can be in these journals. So it's a mix of topic, of the rigor of research, and also increasingly the presentation. So the way that you display the research and explain the research is really important, especially for higher impact journals. It needs to be palatable for a broad audience, right? So if there's certain standards and certain research communities that maybe don't cut it at that level, so there's a lot of effort that goes into making research easily accessible in the figures, describing it in accessible ways that's still highly accurate, but palatable for a broad engineering audience or for a broad science audience in general. So those are the aspects that kind of need to be covered to get the articles into these journals.
Right. So it's almost pulling in science communication, making really complicated research a little bit more palatable in the figures.
Yes, yeah, but it is, so science communication is very important, but for these articles, it still needs to be at a very high level in terms of accuracy, right? So you can't scale it back too much, right? It needs to have multiple levels. It needs to have the level of being able to understand it well. It's like a very accessible introduction that portrays the impact to multiple groups of researchers or research audiences, but then also provide the depth to satisfy the curiosity of the individual, research communities. And I think that that's somewhat of an acquired skill that comes with practice, right? Yeah, I think that's one component of it, right? And then you have obviously the figures. It should be. If you look at the figure set, you should be able to understand the work without having read a single word, right? So it needs to be portrayed in illustrations, in clear graphs. So all of that also plays a big role in getting it into those journals.
When I was prepping for these interviews, looking through different research papers, I really liked reading the ones from your lab because I could just skim through all the figures and you get a complete idea of what the topic is. Still confusing, but easy to get the idea.
Yes, yeah, that's one part of it, right? So you get kind of the idea when you scroll through the figures. It's like, oh, okay, they made this device, it goes in here, and that's kind of what comes out of it, right? But if you want to know more, and what has made this possible that wasn't possible beforehand, you can dig deeper in and really try to understand the details of all of the graphs and illustrations that then kind of portray the novelty, right, of this particular work as well. So there's, as I mentioned, multiple layers to an article like that, and there's a lot of work going into those, a lot of polishing, etc. Maybe more than meets the eye, right? That goes into these type of articles. So lots of hours.
So future grad students who might be interested in coming to your lab, what sort of background would they need to be able to pick up on the research that you're doing?
I think the main thing that future grad students really have to have is the curiosity and the drive, right? To this is pretty broad what we're doing. It covers wireless electronics, antenna design, microcontrollers, firmware, then soft materials, right? What kind of shape do I make to these devices and so they stretch and bend, and what kind of materials can I use in the context of a wearable or an implantable? And then how does this integrate with biology, right? We cover anywhere from these two, right? Helping the neuroscientists, for example, implant the devices and getting the system up and running in a way that they can do their cool research that these new devices enable. Or in wearable cases, we often test them ourselves, right? So it's really to get this full picture of anywhere from making the device and understanding the absolute fundamentals of the electronics materials to the application is all required in order to kind of iterate on what's out there in the current field, but also substantially push it forward. So you have to learn a lot in a short amount of time. It often is helpful if you're already good in one of those things, then you can kind of build the others on top of it. But it's not necessarily needed, right? It's just the aptitude of taking all of this new information in, trying new things, spending quite a bit of time with hands-on work in order to create these devices and test them. That's what I'm looking for. So.
Is it true that you have a treadmill in your lab?
There's a treadmill, there's an ergonometer in the lab. We have like hand dynos and all of that kind of stuff. Yeah, for our wearable devices, there's lots of interesting things. We even have treadmills for mice in my lab. So
that's awesome. That's everything. Okay, and then your field, the biosensors, maybe in general, where do you see it going? You talked about grad students needing to be able to push the field forward. Is there a particular area?
I think I think it depends on what we're talking about. So if we're talking about wearable devices, I think they will become more like your body. They become like a second skin. And some of our newer work, you can see, we call them biosymbiotic devices. They're these the meshes that are tailored directly to your geometry. So we 3D scan bodies and we create a device that's unique to that particular person, where the sensors sit exactly at the right spot, for example, to extract the best fidelity. So I think this will happen more and more as the material science and electronics evolve. In order to be able to do that, I think this will happen more often, and devices will also become easier to wear. These things here, they kind of suck, right? Because you have to recharge them all the time, and then you forget to put them on. And when you do this exercise once, that you really would like to have the stats from, then it didn't work for some reason, or your device wasn't charged, or your phone wasn't closed. So, this kind of stuff will disappear in the future. You just have a small box next to your bed or whatever, your workplace, and that will recharge the device, download the data. So you don't have to think about it, right? You don't even have to take it off. That's kind of where our research goes towards. And with this capability of delivering 24/7 data, we then have the ability to analyze these multimodal data streams to not only diagnose, but also support, like recovery, for example, or support performance, right? Those kinds of things are really important. I think that's what's going to happen in the wearable space over longer periods of time, and increasingly AI, for example, and signal analysis, and the way that we handle the data in general on the hardware side, as well as the software and firmware side, will become even more important than it is at this point in time. For wearable devices, for the implantable devices, I think it's important to outline. My group does, for example, interfaces with the central and peripheral nervous system. So we have published a lot on brain interfaces of the genetics, for example, so cell-specific stimulation, but also recording of particular neuron groups inside the brain in freely moving subjects. And this is currently possible at the small animal scale, but slowly we see the biological tools, the opsins, the viral delivery, evolve towards larger animal models and humans. And that is really exciting to us. We have all of these cool tools that will allow us to manipulate certain neuronal circuits without causing ripple effects throughout the whole nervous system. And that is really exciting, because it would potentially allow, for example, to suppress pain, right? Where you now would need to use opioids, or arrest certain kinds of dysfunction of the brain, for example, during seizures or so, with minimal side effect. And continuously. So I think that's really exciting, that we have that capability, and I'm looking forward in kind of scaling technologies, but also providing new tools to understand the central and peripheral nervous system better. Then we have implantable systems. This should be out in a couple of weeks' time. These are devices that you laminate onto the bone and have a direct interface to the skeletal and muscular system. Pretty cool devices that we can literally grow onto the bone, so they provide long-term capabilities to look at strain after recovering from a surgery, for example, after breaking the leg in a couple of pieces. We can tailor the recovery program, for example, for it really nicely. Or if you have, for example, osteoporosis, and you shouldn't put too much strain on it, these devices come in handy in terms of diagnosis. But lots of interesting stuff that we can do with them in the future. So these are some of the projects that I'm currently excited about. But I think there's a lot more possibilities of interfacing with various organs inside the body and in real time, in order to increase diagnostic capabilities, but also therapeutic capabilities. So we really have the capability to do what is generally known as digital medicine, right? Using this data stream to tailor the strategy of how you fix things or improve things for a particular person, right? A personalized medicine approach.
Yeah, for sure. So you have the implantables with the brain, the implantables on the bones, and then wearables all over. I'll put it all together. It's like complete quantified self data. It's very sci-fi.
Yes, exactly. Yeah. And ideally, you wouldn't even need to, that wouldn't even need to be daily routine, right? The management of all of these
Yeah.
devices should all happen completely automatically. So you just, go about your business, and then, everything, ideally, all of the treatment would happen automatically as well. You just like on a higher level of health without the risk of like getting seriously ill, because you can catch things early, right? I think, well, that's kind of the vision that I'm working towards. I'm not sure if people share the same kind of vision. I think there's variations of this out there, but that's certainly what we work towards, right? Some of the bigger challenges that we're trying to tackle with our research.
This is the lab to be in. Grad students are going to be running to you.
Yeah, I hope so.
So I guess the final question we had is just asking about how you're liking the U of A. You're pretty new, a couple years now, or?
Yeah, well, this is we're now 3.5 years in or so. So the first round of grad students are slowly finishing up in my lab, and I think we've accomplished quite a bit, which is great. So, in terms of university, it's a great place, right? We have all of the collaborators right next door. So the hospital is right over there. If I could look through this wall, I would see it. We have the neuroscientists on campus as well, strong programs there. And for example, orthopedics, right, is one of these areas where we have collaborators, within a couple of minutes walk. So that makes it really exciting for biomedical engineers, right? We need these collaborations to prove that the stuff that we make in our lab really works. So it's critical that we have easy access, and this is definitely the case here. Also, the collaborative spirit at the university is really good. It doesn't matter which department you're from. It doesn't matter, which college you're from. There's no barriers to this collaboration, and that is really important because it allows us to progress very quickly. And I think that's unique about this particular place here. In terms of climate and Tucson in general, it's really nice. Obviously, I like hot weather. I don't like the cold. I grew up in Germany, and if you've been there in like autumn,
Just a
it's
little
absolutely
chilly.
miserable, right? You have no sun for months at a time. This has drastically changed here. It's obviously a good place. I can ride my bike to work every day, and I very rarely get wet, which is good. So.
Awesome. Okay. Thank you so much for taking time to talk to us today.
All right. Yeah, excellent.